Hi, I'm Gary Millette, and this is ELE-110, Electronics for Technicians 1. This is the fall of 2022, and this is topic number 10, Systems and Signals. So let's get started. Electronic system is the title of this slide. So the term system is used quite often when describing a piece of equipment that is built from electronic components. Very often, to better indicate the type of system, we'll add words like audio, video, computer, laser, electronic, communication, digital, transmitter, receiver, control, and so forth. So if one talks about a computer system or a laser system or an electronic system, the type of system is more clearly indicated. Today we even go into further detail in our descriptions of various systems. For instance, we might talk of a Windows-based PC or Mac or Android, indicating the type of OS software, where OS stands for operating system. Or we might talk about a desktop or tablet device to indicate the physical shape factor or footprint of the device. My cat has shown up. If you see a tail wagging across the screen, it is my cat. System components. Well, the question might be, what does a system really consist of? Today, an electronic-based system tends to consist of some basic fundamental components or subsystems. Very often, well, 100% of the time, we need a power supply or a source of power. We need some type of man-machine interface. We call that an MMI, or human-machine interface called an HMI. Very often we'll have a system control unit, which would be a microprocessor or microcontroller. And then we have the delivery portion of the system. That is the part that actually performs the given function. So here's a block diagram of an electronic-based system. And we come up with this block diagram to kind of take and, indicate what the various subsystems are. So what it shows, the power supply is connected to all of the subsystems. So the user interface, the computer network interface, the device hardware, all have signals coming from the power supply. There's voltage to supply power. And notice the controller and software down below have these lines from the power supply. So the power supply provides power to everything in the system. Furthermore, there are signal pathways or connects between the various subsystems. So you might notice the bold black line there with the arrows from the user interface, controller, device hardware, software, and computer network interface. Also notice the computer network interface has a two-way connection. So again, that's the basic electronic system block diagram. Let's take a closer look at some of the details of, say, the power supply. So presently, every electronic device requires DC voltage to operate. Turns out that semiconductor-based active devices perform their functions by controlling the flow of electrons. So typically, to be able to control the flow of electrons, semiconductor devices must be biased in a certain way to facilitate their functioning. This is typically done through the use of different levels of DC voltage. So where does the power supply get its power? Well, the typical system power supply is powered from the AC voltage delivered by the local power company. So you plug it into the outlet and you get 120 volts AC in the United States. Other countries have different voltages. And again, that's AC. That's how we deliver our power because it's most efficient to deliver it that way. Electronics needs DC, so it turns out the power supply converts the AC voltage to one or more DC voltages that will be used to power the system's subsystems. Now, digital devices, things like logic and microprocessors, typically require 5 volts DC or less. Today, 3.3 is quite common. While active devices like transistors or other analog ICs like op-amps might require, say, either plus or minus 12 or plus or minus 15 volts DC. Certainly, if the system consists of devices that supply any appreciable amount of power, and recall from the last topic that power equals I times V, the power supply will have to provide either an extremely large amount of current I at a low voltage or much higher voltage with a lower current. Today, many systems employ some form of system power management. When the system is not in use, it goes to sleep. That is, it goes into a reduced power mode where subsystems are powered off when not being used. Typical examples are cell phones and PC screensavers for your laptop or desktop computer. Today, many devices are used in a mobile fashion. Mobility is the new term we use, and therefore are battery operated or powered. These type of devices tend to use sophisticated power management schemes to prolong battery life. Think of your cell phone. Also, systems that must be constantly on usually require some form of emergency battery backup systems that automatically take over during a power outage. Some final thoughts on power supplies. The first thing one should do when troubleshooting a malfunctioning system is to determine whether or not the power supply is functioning correctly. Today, many system power supplies will have LEDs that indicate their operation. These LEDs could be, red, green, or yellow, that indicate the correct or incorrect operation of the power supply, with green being correct operation and red being a fault. So here's some typical power supplies. We call this an open frame one on the left-hand side. You might notice in the bottom of that PC board it says minus 35 volts and plus 35 volts, so it looks like that puts out a 70 volt power DC voltage. There are 6 big electrolytics there. There's a toroid inductor, which probably is a transformer, to the left of the electrolytics, and there's a bunch of probably rectifier and power transistors to the right on the edge of the right-hand side of the printed circuit board. The enclosed power supply to the right of that is one that you could order online, and you might notice it looks like a couple of LEDs. It looks like an orange and a green LED next to the terminals for connecting that power supply. Here's a high voltage power supply for a laser on the left-hand side, and it looks like a modular power supply for a tower type computer on the right-hand side. What about the man-machine interface? Well, the man-machine interface or human-machine interface is a means by which one controls the operation of the system. And there can be many different versions of this. In some cases, this could be nothing other than an on-off switch or key for a system that needs very little human intervention. You just turn it on. In other cases, there could be many inputs and many outputs that are required to control the system and indicate ongoing system operation. So in some cases, the MMI is a keypad, and the indication of system operation is nothing but the glow of an LED, and again, could be green, yellow, or red. Depending upon the system's intended function and complexity, a vast array of input-output devices are possible, from keyboards to game controllers to extensive color graphics displays with sophisticated touchscreens. Now, your life experience has brought you into contact with numerous different types of complex systems, each with their own particular MMI. So here's some examples. I got pictures of 4 different things here. There's a remote control in the top left. There's a smartphone in the top right. There's an oscilloscope below the smartphone with many dials and controls on it. And then there's a, looks like a touchpad type of controller for maybe a CNC machine on the left-hand side. What about the system controller? Well, today most systems employ some type of microcontroller to aid in the control of the system. The use of a microcontroller for this purpose has spawned the terms embedded control and embedded controller. So some of the details of the system controller are, it is possible that there are electronic-based systems in use today that do not presently employ embedded control. But the next redesign of that product most likely will. If you follow the popular press, you have heard about AI or machine learning, the next big things in smart systems. By the way, AI is what? Artificial intelligence. Today, the number of microcontrollers that are manufactured and put into products is many, many more times than the number of microprocessors produced for PCs. There are billions of microcontrollers manufactured every year. A microcontroller is usually a self-contained unit with onboard memory, input-output ports, and circuitry that can convert analog signals into digital data and vice versa. A microcontroller is typically programmed to perform a set of tasks that are required to control the system's operation and functions. As mentioned earlier, the promise of ML, machine learning, and AI, artificial intelligence, might be a game-changing paradigm as we go into the future. Excuse me. To take advantage of the internet, excuse me, more and more products are providing electronic access to the system's embedded controller so that one might provide remote diagnostics, software updates, or remote access for user convenience. On the downside of this is now the need for cybersecurity to prevent access by bad actors taking over your system. One should not confuse this aspect of system operation with other internet/system operations such as online game playing. The system's controller can modify system behavior and characteristics. In the future, many feel that it will be commonplace for the system controller to enable the system to evolve. That's shades of the Terminator or Arnold Schwarzenegger, the famous "I'll be back." The newest uses of embedded controllers combined with internet connectivity is in the implementation of cyber-physical systems. There's some representative hardware for a cyber-physical system. Cyber-physical systems are control systems that work in real time. In other words, we can control things as they happen. Other system subsystems, well, the other systems are used to provide the basic functions that the system has been designed to perform, and therefore unique to the system's purpose. The PC is a typical system. Most of our electronics, computer, and laser students should have little trouble identifying the various subsystems and describing their basic functions. This is certainly not the case with another popular device, the high-definition TV. If I was to take apart a computer case, I could probably spot the memory and so forth, certainly the CPU board. However, if I took off the back of a flat screen TV, I'd probably find one circuit board, and I'd be hard pressed to identify any of the components on it. Here's a subsystem, a modular PC power supply for most likely some type of tower type computer. You can see the Molox connectors that power the big one there. The one was 20+4 is what's get plugged into the motherboard, and the other devices, other Molox connectors, connect to hard drives and other portions of the computer. Here's a older Cisco model 1841 router board, and I just show this to you. You can note the modular power supply on the left and the cooling fan and the motherboard like printed circuit board that makes up this router. And it turns out that it's similar to a PC. How about under the hood of a modern vehicle? Here's a Ford Mustang. A picture of the under the hood. Today's vehicles typically have upwards of 100 microcontrollers controlling their operation with numerous sensors and actuators contributing to the vehicle operation. So here's a close-up for this gasoline engine powered Ford Mustang. We have an airflow control, and that's that little silver motor thing there with the connector going to it that controls the flow of air going into the gasoline engine. That brings us to a new topic, basically signals. So let's start with this. Should we shift gears a little bit? Now, almost all electronic-based systems deal with the processing of signals. Signals that may be either analog or digital in nature. Consumer electronics devices that record, play, or display multimedia content stored in digital form, that is things like DVDs, CDs, MP3 players, movie files, and iPods, and so forth, must process this information to perform their intended function. Communication systems that allow us to transmit multimedia content around the world or to our next door neighbor, we call that telecommunications, all process signals to perform this function. So we typically use a sine wave as a starting point to study signals. Many applications deal with signals made up of many different types of sine waves. Digital signals, rather, on the other hand, often take the form of pulse waveforms. So we start with a sine wave, and we have some graphical pictures here, depictions of it. So the sine wave is a naturally occurring phenomena that is used extensively in industrial applications. Man-made sine waves are produced by either electrical machinery, we call those generators, or electronic oscillators. So figure 11.2 is a graph on one cycle of a sine wave, and figure 11.1 is a symbol for a sine wave voltage source. So we see the blue tinted circle with the sine wave inside, that's a sine wave voltage source. To the right of that we have a red sine wave and an XY axis which shows voltage versus time. And it shows a positive maximum and a negative maximum. So we talk about the polarity of a sine wave, here shown with a shaded area above the positive, well, 0 is the ground where the time is indicated, and it turns out above that would be positive and below that line is negative. So this shows that blued in area is a positive alternation of the sine wave. So when the sine wave is positive, conventional current flows as shown, electron flow is just the opposite. So the circuit diagram on the right hand side shows the sine wave generator with plus to minus, the plus on top and minus on the bottom, and it shows current flowing from plus to minus, which we know is opposite of what the electrons really do. The electrons go from minus to plus. So this is the positive alternation, and notice it goes up to a peak, then back down to 0, and then we have the negative alteration. So the sine wave is now negative and the current reverses direction. So the diagram to the right shows the sine wave generator plus on the bottom, minus on the top, and again conventional current going from plus to minus, but again the electrons are really going from minus to plus. So we talk about the characteristics of a sine wave, we talk about the period of a sine wave. So the time required for a sine wave to complete one full cycle is called the period t. So these two pictures here show in part A of figure 11.4 one sine wave with a period t of time. To its right is 3 sine waves, and it turns out that again in the right hand picture each sine wave has the same period. So here's an example that says what is the period of sine wave in this figure 11.5, and it shows as the sine wave goes through one complete cycle, that is positive to negative alteration, in 4 seconds. So there's 3 sine waves shown there. It takes 12 seconds for that to occur, and the period of that for one sine wave, the period t equals 4 seconds. So if I want to make or measure the period of a sine wave, there are numerous ways I could do it. Figure 11.6 just shows a sine wave, and over to its right, figure 11.7, it shows we could go on the positive side of the sine wave, we go peak to peak or 0 to 0, and then down below that, the negative side of this part of the sine wave, I could go peak to peak or 0 to 0 also, and that would give me the period t. What's more common is the idea of the frequency of the sine wave, and the frequency is the number of cycles that a sine wave completes in 1 second. So on the left here, figure 11.8, we see 2 cycles in 1 second, so that would have a frequency of 2 hertz. To its right, we have, it looks like 1, 2, 3, 4 cycles in 1 second, so that would have a frequency of 4 hertz. The unit of frequency is hertz. 1 hertz is 1 cycle per second. So what is the relationship of frequency and period? Well, turns out there are a reciprocal relationship between frequency and period. So we have 2 equations here, f equals 1 over t, or t equals 1 over f. So this concept's very important. A signal that changes slowly indicates a low frequency. A rapidly changing signal indicates a high frequency. So here we see 2 sine waves. The question is, which has a higher frequency? Well, that's very easy. It's the one with the more cycles. If they both occur in 1 second, as you look at the diagram 11.9, it turns out they both do. On the left-hand side, I've got 3 cycles in 1 second. On the right-hand side, it looks to me I've got 5 cycles in 1 second. So the higher frequency is on the right-hand side, 5 hertz. How do we generate sine waves? Well, one of the easiest ways to do is use an AC generator. So AC may be generated using the principle of induction. That's Faraday's law. This shows a magnet with a north to south pole, so there would be magnetic lines of force between the north and south pole. and it would turn out that this shows a loop of wire which is being rotated. So there's a mechanical drive that's causing that loop to rotate within this magnetic field. And it turns out there's two slip rings that allow the voltage generated to go through a load, and it turns out this shows that the loop's being turned in a clockwise direction. Now in the next slide, here's more detail. So here in part A, the upper left, we have the first quarter cycle, the first 90 degrees of rotation of the loop, and we see that we have on the oscilloscope there the first 90 degrees of the cycle of the sine wave. If we go over to the top right, we see the second quarter cycle of now 180 degrees of the rotation loop, and we see the top or positive alteration of the sine wave. We go to the bottom left-hand corner, we see another 90-degree rotation, and now we've got 270 degrees, and we see 3/4 of the sine wave. And finally, in the bottom right-hand side, we see 360 degrees of rotation back to the start, and we see 360 degrees of the sine wave, one complete sine wave. So it turns out that, again, one rotation, the 360 degrees of rotation, is equal to one sine wave. So in the lab, we actually have modern arbitrary function generators. Here's a one that uses digital signal synthesis, but nevertheless, you can create just about any frequency here within limits of this model 33500B Keysight waveform generator. This is in room 617. These devices exist. In room 625, we have less expensive Tektronix arbitrary function generator. So voltage values of sine waves, it turns out there's numerous ways to express the amplitude of a sine wave. Here we see on the left-hand figure A of figure 1115, notice we call it time T1, we got voltage V1, time T2 is voltage V2, and time T3 is voltage V3. We also have time T4, which is voltage V4, which is negative, time T5, which is voltage V5, which is negative, and time T6, which is voltage V6, which is negative also. On the right-hand side, we have a particular sine wave that has a 10-volt positive peak and a minus 10-volt negative peak. And it turns out that in this sine wave, it takes 20 microseconds for it to complete. And it turns out after 1 microsecond, the voltage is 3.1 volts. After 2.5 microseconds, the voltage is 7.07 volts. After 5 microseconds, or 1/4, or 90 degrees, the output is 10 volts, the maximum. At 10 microseconds, it turns out the output is 0. At 11 microseconds, it's minus 3.1 volts. At 12 microseconds, minus 5.9 volts. And at 15, or 3/4 of a cycle, it's the maximum negative or minus 10 volts. So the graphic depicts instantaneous values of the sine wave. And it turns out that that information is available to you, by the way, on any handheld electronic calculator, what the voltage is for various times of the sine wave, or fractions of a sine wave. Now, when we talk about the amplitude of a sine wave, we either talk about the peak amplitude or the peak-to-peak values. And we have two figures here. 1116 shows the peak value. It's got V sub peak for positive, or V sub peak for negative. And they would be equal to one another. And to the right, we have equations V. Voltage peak to peak would be 2 times voltage peak. And down below in figure 1117, we see going from the positive peak to the negative peak, we call that voltage peak to peak. So a common way to describe a sine wave is to either give its peak voltage or its peak to peak voltage as shown here. Now, it turns out, interestingly enough, that if we have a meter for an AC signal, it will measure the RMS value. So the term RMS stands for root mean squared. This is an effective value which correlates the heating effect of a sine wave with a DC voltage. Most AC voltmeters display RMS values. So this diagram here shows you a sine wave source with a output VRMS and a resistor, and the resistor is radiating heat. Excuse me, and it shows the temperature being measured of the radiated heat, Then on the right, we have a DC source with voltage DC is equal to VRMS, and we get the same amount of heat. So RMS was invented really to give you a way of comparing AC voltages, the heating effect of AC voltage versus DC voltage. The voltage supplied to one's home or apartment is given as an RMS value, and basically it's 120 volts RMS. Now, 120 volts RMS in peak to peak is shown here. Basically, the peak to peak voltage is 340 volts for 120 volts RMS, shown in this diagram. So how do you convert between RMS and peak to peak values? I got a lot of equations here in this slide. I would tell you you could Google any of these at any time. So to try to memorize them and so forth is not all that important. I will point out that the first equation, the top left there, volts peak to peak is 2.828 times voltage RMS. You might consider that 2.828 is actually 2 times the square root of 2. The middle top, I've got voltage RMS is 0.707 times voltage peak. And over to its right, voltage peak is 1.414 times voltage RMS, where again 1.414 is the square root of 2. And then finally down the very bottom equation, voltage peak is a voltage RMS divided by 0.707. 0.707 is the square root of 2 over 2. So again, you can take and get those from Googling them. Average value. The average value of a sine wave is 0. It's equally positive as negative, so it turns out the average value, if you calculate it, would be 0. So that's kind of doesn't tell you much of anything. So what we do is we take the average value of a sine wave is defined over a half cycle to give a non-trivial value. And of course, these equations, you got to use calculus to derive these results, but let's just say that voltage average is equal to 2 divided by pi times voltage peak, or voltage average is that 2 over pi works out to be 0.637 voltage peak. So here's an example, and this one shows, this is figure 1119. This is determine the values of peak, peak to peak, RMS, and average value for the sine wave. So it looks like it goes up to plus 4.5 and down to minus 4.5. So the peak to peak would be 9 volts. If I take and multiply 0.707 times the voltage peak, I get 3.18 volts. And if I want to find voltage average, I take 0.637 times voltage peak, or I get 2.87 volts. What about the angular measurement of a sine wave? Well, it turns out that, again, there's a one-to-one correlation between a sine wave and the rotation of something in a circle, or 360 degrees. So this shows the loop of a generator and the sine wave that would be result from this generation of AC voltage as the loop spins around 360 degrees. Now, when the loop starts at 0, it turns out it's parallel to the lines of magnetic force and therefore not cutting any, and therefore wouldn't generate any voltage. But as the loop goes up towards 90, now it's cutting more, the maximum number of loops, so the output at 90 degrees is highest. When it goes down to 180, it's in parallel with the magnetic lines of force, not kind of cutting any and having 0 output volts. Then as it goes through 270, it's going the opposite direction it was as it was going through 90, and so the voltage is opposite in polarity and maximum, which you see on the diagram of the sine wave voltage on the right. So note the relationship between the angular position of the loop in an AC generator and the sine wave. So this slide's called angular measurement. A degree is an angular measurement of 1/360th of a circle. A radian is defined as the angular measurement equal to the movement of one radius around the circumference of a circle. 1 radian is equal to 57.3 degrees, and there are 2 pi radians in 360 degrees. So you see that diagram there where 57.3 degrees is the value of 1 radian. So here's a figure that shows degrees in radians. 90 degrees becomes pi over 2 radians. 180 degrees is pi radians. 270 degrees is 3 pi over 2 radians. And again, the graphic shows the sine wave labeled with degrees and with radians. So is there a formula for the sine wave? Sure there is. So far, the sine wave has only been shown graphically. It may also be represented by a mathematical equation. So here you see a sine wave that has a peak value of A. We see an angle of theta, which is gives an output of y at that angle of theta. And the sine wave may be written mathematically as y equals A sine of theta, where again, you can get the instantaneous value of the sine wave at any value of theta. In this equation, y is the amplitude, the instantaneous value of the sine wave, and A is the peak amplitude. So here's an example. At theta equals 60 degrees, the output is 8.66 volts. If at 90 degrees, the output is going to be 10 volts. Using the sine wave equation, one may determine the instantaneous value of the sine wave at any point on the curve. An electronic calculator has the capability to give the value for either a degree or radian value. So, one thing we've seen so far, all these sine waves started at 0. So here we have two diagrams in figure 1130 where we have shifted sine waves. In A, it turns out that there's a angle phi, which means the sine wave is started after 0, time equals 0. Or in B, we have a sine wave which is shifted to the left by an angle phi, which means it started before the time equals 0. So note the sign of the shift, negative for delay and positive for a lead. And there's two equations down there. Y equals A times the sine in parentheses theta minus phi, or Y equals A times sine in parentheses theta plus phi. So here's an example. It says determine the instantaneous value at the 90-degree reference point on the horizontal axis for each sine wave voltage in figure 1131. And we have wave A, B, and C. A is green, B is red, and C is blue. A starts at 0, whereas B, the red one, starts at minus 20, and C, the blue one, starts at plus 45 degrees. So I'm not going to go over the solution, but you should go over that to satisfy yourself that at 90 degrees, the value of the green, red, and blue waveforms are given as shown in the solution there. What about Ohm's and Kirchhoff's law in AC circuits? Well, the circuit laws introduced for a DC also hold for AC. We see a resistor here, a sine wave generator, and the voltage across that resistor would take on a sine wave shape, and the current also would take on a sine wave shape. Here's an example of Ohm's law. So it says determine the RMS voltage across each resistor and the RMS current in figure 1133. The voltage source is given as an RMS voltage. So it says 110 volts is V sub S, and that's RMS. There's an R1 1K and an R2 of 560 ohms. In the solution, our total resistance is 1.56 k ohms. To find the current, the RMS current, we divide the RMS voltage, 110, by 1.56 k ohms and get 70.5 milliamps, which would be an RMS value. If we want to find the voltage across each resistor, we use Ohm's law to multiply that resistance by the RMS current, and we get 70.5 volts across R1 and 39.5 volts across R2, which add up to 110 volts, the applied voltage. What about Kirchhoff's law for an AC circuit? Kirchhoff's law for DC says all the voltage drops add up to what's applied. Well, the same thing happens for AC. You see the voltage across R1, R2, and R3 add up to V sub S, what is applied by the blue AC signal generator there. Now, what about superimposed DC and AC voltages? It's very common to find DC and AC voltages combined in practical electronic circuits. This diagram shows a voltage source, VAC, which is in a sine wave. It shows a DC battery, VDC, and a load, R. So the voltage across the resistor is going to be the voltage AC plus the voltage DC. And what that looks like is shown here, figure 1137. It turns out in this case, the peak voltage of the AC signal is less than the DC battery voltage. And what we have is what we call a unipolar signal, that the voltage now across the load is always positive. If the voltage of the AC signal was bigger than the DC battery, and my cat is back, so watch out for the wagging tail here, it would turn out that you would get a bipolar signal across the load where the voltage, in this case, most of the time is positive, but there's a short period of time it goes negative. So in both cases, the AC sine wave is offset by a DC level. Our last topic is non-sinusoidal waveforms. So there are many other types of time-varying waves used in electronic systems. We have pulses, triangular waveforms, sawtooth waveforms, ramp waveforms, and many others. Interestingly, each one of these waveforms consists of what? Harmonically related sine waves that when added vectorially create the particular wave. So there aren't really waves other than sine waves. These things, when we look at them on oscilloscopes, which we're going to talk about in a little while, look like pulses. They look like triangle and sawtooth waves and ramps and so forth, but they're really combinations of sine waves. So here's pulse waveforms. This graphic shows several ideal pulse waveforms. Note the various waveform characteristics. So figure 1140, ideal pulses, a positive going pulse, starts at 0. We call that the baseline, goes up to some amplitude. It's got a pulse width, how wide it is. It's got a leading or rising edge and a trailing or falling edge. A negative going pulse starts from 0, that's the baseline there, and goes negative. It's got a pulse width, it's going to have a leading or falling edge and a trailing or rising edge. Those are ideal pulses. So repetitive pulses are pulses that occur over and over again. So here in figure 1142 we have A, B, and C, and it turns out that actually A and C are similar to one another. There's a pulse width, T sub W, and a period of the pulses, that is from leading edge to leading edge of T. And it turns out that they're not the same. The width of the pulse nor the period are the same. However, in B, it looks like the width of the pulse and is 1/2 of the period, and we would call that a square wave. C, diagram C, looks similar to A, except there's more pulses per second. So most pulses are repetitive in nature. The rate at which the pulses repeat is known as the pulse repetition frequency, or PRF. The pulse repetition frequency is given by 1 divided by T. Remember that reciprocal relationship between frequency and period. So, a very important aspect of pulse waveforms, what we call the duty cycle. An important characteristic of any pulse waveform is a duty cycle is given by the percentage of on time to the period of the pulse times 100%. So here we have an example which shows you the pulse is on for 1 microsecond and the period of the pulse is 10 microseconds. So it turns out the percent duty cycle is 10%. It's on for 10% of the time, off for 90% of the time. What about square waves? So a square wave is a special case of a repetitive pulse waveform that has a duty cycle of 50%. So it's on for half the time, off for half the time. Square wave is actually a very common waveform. What about triangular and sawtooth waveforms? Well, here we see some ramps and then a triangular waveform down below. So I got a positive ramp with a slope of V over T. I've got a negative ramp with a slope of minus V over T. And it turns out my triangular waveform looks like a combination of a positive and a negative ramp. And here's some sawtooth waveforms. There's a unipolar sawtooth in the top one in figure 1149, and figure 1150 is an alternating or bipolar sawtooth waveform. These waves are oftentimes created by charging a capacitor with a constant current source. It gives a nice linear waveform. Now, we mentioned harmonics before. Now, I'll repeat this. All repetitive waveforms consist of the fundamental frequency and some combination of the harmonics. Harmonics either odd or even, that is integral multiples of the fundamental frequency. For instance, n times f, where n equals 1, 2, 3, 4, 5, 6, and so forth. The first time you hear this, it's usually very hard to wrap your head around this. Here's a figure 1151 that shows odd harmonics produce a square wave. So they show the fundamental, that's a dotted red sine wave, and they show the third harmonic. And actually, the amplitude of the third harmonic is 1/3 the amplitude of the fundamental. And it turns out that they show them added together to give a blue sum, in figure A there. Now that's not a square wave, it kind of looks like a couple teeth as a matter of fact. But then in B they show now the fundamental, the third and fifth harmonic. And by the way, the fifth harmonic would have an amplitude of 1/5 of the fundamental. And notice now the sum, we have a more squared up looking wave. To the right of that in C, we have the fundamental plus the third plus the fifth plus the seventh harmonic, and we're getting closer to an ideal square wave. If we have an infinite number of odd harmonics with the correct magnitude, it turns out that we would create a square wave. So it turns out that, again, this kind of shows you that the harmonics are what make up these, these periodic waveforms. If you go online, you go to YouTube, you can probably find some videos of people that show you how this occurs. As you go through your study of electronics, we're going to show you things called spectrum analyzers that will actually show you the waveforms that make up, these repetitive waveforms. So, what do we use to look at waveforms? Oscilloscopes. This is not the type of oscilloscope we have in room 617, but we do have touchscreen digital scopes in room 617 lab. And this just shows that these look very complex looking devices, and you'll get to use them eventually. Actually, in room 625, we have less expensive digital oscilloscopes, and as I mentioned before, less expensive arbitrary waveform generators. You may come across handheld scopes for field use. These are all Agilent handheld oscilloscopes. 4 of them on the right-hand side, and one blown up a little bit on the left-hand side there. Looks like a digital multimeter, but it turns out it is a handheld oscilloscope. And it turns out we have PC-based oscilloscopes, where it turns out we have a device like this. This device is Pico technology. By Pico technology is connected to a PC or laptop, usually, excuse me, via USB, and this displays waveforms like traditional scope. So it's a lot less expensive than a scope because you're using your PC or device for the display. And this is what you might see on one of those Pico scopes. Numerous windows. We can see the waveforms displayed by time, and actually it turns out in the bottom right hand corner we have a waveform which is a spectrum analyzer display of some repetitious waveform. And we also have like Digilent, for instance, from analog devices. There's an analog discovery device which uses your PC, and it's a PC-based lab scope. So you can take and look at the output of a small, circuit like the one showed here in a breadboard. Some final thoughts about oscilloscopes. The oscilloscope shows how a signal changes with time. That is, it displays signal amplitude versus time. Hence, it is said to display the signal in the time domain. Today's digital storage oscilloscopes, or DSOs, are extremely intelligent and also have computer interfaces, things like RS-232, GPIB, LAN, and USB connections that allow them to be controlled locally and remotely. Furthermore, the data that creates the display is also accessible. So today's modern oscilloscopes are quite complex measurement devices. And that ends this presentation.